All right, I think I might go ahead and begin. Thank you everyone for joining us today for our fourth SEDS Online student webinar. My name is Sarah Giles and I'm a PhD student at Columbia University in the US. I've put together and I'm really excited to host our talks today from four awesome student presenters who have amazing research on exploring sediment transport dynamics from source to sink. So before we start with that student webinar, I already want to plug our next one. And if you guys can help distribute the word about the next theme, which will be new insights into biogenic sedimentation. If you know of a great student or you know of a professor who has students on that topic, please, please, please refer them to our website and to our social media so that they can submit their research idea. This is a great opportunity for students to show their work and to get the community, the global community's ideas and suggestions on what they're working on. So please get that out there. So I also want to thank our sponsorship from IAS, which allows all these resources for free, which check our website. There's so many other amazing events and coffee breaks that are really exciting and cover a range of topics. So please check those out. So I won't make us wait any longer today. And so we have a really exciting series of student talks. Again, they'll be discussing on exploring sediment transport dynamics from source to sink. They'll be giving 10-minute talks and we'll have 4 of them. And they'll be followed each by 5 minutes of questions. So feel free to just post your question in the chat and I will read it out to them afterwards. But please, if you can, indicate which student you're addressing it to, and please put your name and your location so we can know where you're asking from. And if we don't reach any of the questions, I don't get to it in time, we will return at the end and ask all the students in kind of a panel format the remaining questions. So please, we will get to them, don't worry. So if we're all ready to go, Nikhil, if you will start us off. Our first presenter will be Nikhil Sharma, a PhD student from the University of Geneva, and he will be discussing sedimentary sequences from the Pyrenees. So Nikhil, I'll stop sharing so you can.
Right.
Perfect. That's full screen. Thanks, Nikhil.
Thank you. And hello, everyone. So today I'll be presenting the work I've been doing as a part of my PhD project on the Escanilla formation in the southern Pyrenees in Spain. And the fundamental question that my project revolves around is to try and understand if climatic signals do leave an imprint on the stratigraphic architecture. And this would be through 3 primary variables, namely water discharge, QW, sediment supply, QS, and median grain size, D50. And this would be in the form of changes in paleoslope. So as water discharge increases, the resulting river profile would be a much flatter one. And as water discharge would decrease, the resulting profile would be a much steeper one. One approach of testing this could be through numerical models. And there have been studies which have looked at this already. Here we have an example from the Simpson and Castle-Todd numerical models, where a 100-meter long river profile is modeled against sinusoidal water discharge variations. And what we observe is as the water discharge decreases, in the second plot here, we see that sediment begins to accumulate upstream, and we observe that the slope increases. As water discharge begins to increase, the sediments which are stored upstream are flushed downstream, and the resulting profile would be a much flatter one. So to summarize this, with low water discharge, low sediment supply, we have resulting higher slopes. In the other case, as we have high or increasing water discharge, there would be higher sediment supply, and we would expect lower slopes. So the main hypothesis that I am testing through my project is to look at if upstream factors control fluvial architecture through changes in water discharge and sediment supply. And the second approach, apart from numerical models, could be to quantify some paleohydraulic parameters for a natural sediment routing system. And for this purpose, we use the Escanilla sediment routing system of the middle and upper Eocene age, which is Bartonian, around 40 million years. And we have a complete source-to-sink river profile. So we have Cis, which is the proximal part of the system, then La Square, which is an intermediate part of the system, and finally Olson, which is the distal part of the system. And my talk today focuses on the data we have so far from Olson. So we've been on the field and we have mapped out what we call fining upward sequences, where each fining upward sequence has this thick, laterally extensive amalgamated channel body, which is 10 to 15 meters thick. Above this amalgamated channel body lies a floodplain dominated interval with isolated channel bodies, which are much thinner. And for each of these sequences, we have collected grain size distribution and data for flow depth from both the amalgamated and the non-amalgamated intervals. For the grain size distribution, we use the Woolman sampling procedure, where we measure at least 100 clasts for their longest axis. And we have predominantly done this using ImageJ, an image analysis software. So on the field, we would take pictures of conglomerates or the gravel at the bottom of the channel, and then have a virtual grid overlaid on it, and then do point counting to obtain the median grain size or the required grain size percentiles. For the flow depth estimates, story thickness can act as a proxy for depth estimates from ancient systems. So here we have a beautiful example of multi-story stacking pattern in isolated channels, that is the non-amalgamated interval. And here, the thickness of a story marked by the arrows here would give a minimum depth estimate. A second approach for flow depth estimates, or the best estimates that one could have for ancient flow depth, come from channel plug or lateral accretion deposits, but these are rarely preserved in the stratigraphic record. Here we have a good example of a channel plug, and similar to the story thickness, in this case, the thickness of a channel plug would provide a minimum estimate of the flow depth. The story thickness and the channel plug thickness is then corrected for compaction, and then after we obtain the bankful depth. The median grain size and the bankful depth estimates are quite important because these are then used to estimate paleoslope. For paleoslope estimation, we use this empirical equation, which gives a relationship between the channel slope, median grain size, and bankful height. And then we have 3 empirical coefficients. Using the bankful depth, we can also calculate the flow velocity using the Manning's equation. And this is then used to estimate water discharge. For the bed load sediment flux, we use the Mayer, Peter, and Muller equation, which again uses the median grain size, bankful depth, and the slope estimates. So coming to the results, on the extreme left here, I have the stratigraphic log with the 3 fining upward sequences that we focused on. At the base of each sequence is the amalgamated unit marked by A, and above which lies a non-amalgamated interval marked by NA. Then I have my field observations. First is the grain size, the median grain size, followed by the bankful depth, HPF. And using these data is then the estimated paleoslope. Each of the black dots here represents an individual observation. The vertical bars here are the median values, and the white circle, which is connected by a red line, is the mean values that we have. Probably the most striking observation that one could make by looking at this figure are these strong changes in water depth from amalgamated to the non-amalgamated interval. So for the first sequence, we go from flow depths of 4 meters to an average of about 2.5 meters. And this change from higher flow depths in the amalgamated and then lower flow depths in the non-amalgamated pretty much follows for the rest of the sequences as well. For the paleoslope, we have lower slopes in the amalgamated interval and then an increasing trend in the non-amalgamated interval. Sometimes the trend is very subtle and perhaps also not so clear, but the strongest or the highest slope estimates come from the non-amalgamated intervals, while the lower slope estimates are from the amalgamated interval. Here I present the first column is the bedload sediment paleoflux, followed by the water discharge, and then the estimated paleoslope equation. So for the first sequence, or in general, we observe higher water discharge rates for the amalgamated units, followed by a decrease in sediment flux in the non-amalgamated interval, which follows the trend follows for the rest of the sequences as well. In water discharge, the trend is much stronger, higher water discharge rates in the amalgamated interval, then lower in the non-amalgamated, and then so on. For the slope, we've just seen this, lower slopes in the amalgamated, and then higher slopes, and or rather increasing trend in the non-amalgamated interval. To explain these strong changes in the water discharge that we see, one possibility of explaining this could be in the form of eccentricity-driven discharge variations, which thereby control the changes in paleoslopes that we observe. And this follows the physical rationale that eccentricity maxima corresponds to more intense and extreme events, be it either wet or dry, and eccentricity minima are periods of stable seasonality. So for the amalgamated intervals, these would probably be linked to increasing eccentricity, where we have higher water discharge and then low seasonality during the eccentricity minima, and thereby lower water discharge in the non-amalgamated interval. If I have to summarize my talk, I think there are 4 key takeaways. The first one is the use of paleohydraulic reconstructions as a potentially powerful tool to study sedimentary sequences. The second is we are the first to quantify paleohydrology of the Escanilla formation. And through our results, we have successfully tested our hypothesis of slope change in a fluvial system by documenting lower paleoslopes during high discharge rates. And we hypothesize that variations in discharge are driven by eccentricity changes. Yeah, so I will stop here. Thank you.
Perfect. Thank you so much, Nikhil. So now the chat is definitely open for any questions. I will read them out, but I will start us off if that's okay. I have quite a few. That's amazing research. So my first one was when you showed that outcrop photo of the amalgamated channels, there was a bunch of ones that had erosive base, and you talked about measuring their thickness to get their paleo depth estimate. And my first question was, how do you account for those different erosive bases of those channels that might actually cut out some of your thickness of your channel?
Yeah, that's true. There are definitely these erosive bases. That's why the flow depth estimates that I get are a minimum depth estimates. And then the most I think I can account for are these error bars, standard error from multiple measurements to make sure I have standard errors. But yeah, these are minimum depth estimates and not the actual flow depth.
Perfect, thank you. And so you have a question here in the chat from Jay Reimer, who's from Amsterdam. How do you discriminate between tectonic-induced sediment input and climate-induced sediment flux?
Right, that's a very interesting question. So there definitely would be some tectonic influence on my sedimentary flux or water discharge. But I think there's a difference in the time scales that, so my sequences are we estimate them to be around 400 kilo years. If tectonic does play a role, it would be a magnitude higher in the duration. So I think it rather seems unlikely that the dominating influence is of tectonics in this case.
Perfect. We have another question here from Gary Hampson from London, and he says, "Hi, Nikhil. Thanks for a really interesting talk. Do you see any variations outside of the channelized sandstones to support interpretive variations in paleohydrology or climate? For example, differences in styles of overbank deposits, paleotypes, etc."
Yeah, I'm sorry, I'm not sure if I really understood the question.
Can I read it one more time, Nikhil?
Yeah, maybe if you read it one more time.
Yeah, perfect. So he says, do you see any variations outside of the channelized sandstones to support interpreted variations in paleohydrology or climate? For example, differences in the overbank deposits or the paleosol types.
Oh, so for the paleosol and yeah, the overbank deposits, so a second part of my PhD project, which I don't present here, is to do some geochemical analysis on these soils and then have some isotopes and then compare it to the water discharge variations that I observe. So that is currently work in progress. And yeah, just stay tuned. And I think the results should be out soon.
Perfect. And we have one more question, and then we'll move on to our next presenter. This one is from Maria Jensen from Svalbard, Norway. And she says, "Thank you for a great talk. Are your calculations depending on whether you have lateral control on channel width?"
Oh, yeah, that's a good question. Yeah, so channel width is an interesting parameter that is hard to quantify, especially for the amalgamated intervals. And so actually I do have a supplementary figure. So for the channel width, I use this Bridge and McKay 93 empirical equation. And this depends on the bankfull depth estimates that I have. And I have done that for the amalgamated and the non-amalgamated intervals for all my sequences. The two end bars here are from the widths that were estimated in one of the previously published works in the same area. Well, our estimated widths are much lower than these ones, but in general, we observe higher widths in the amalgamated channels and then a decrease in the non-amalgamated, which is pretty much, which is true for the rest of the sequences as well.
Perfect. Thank you so much, Nikhil. Wonderful presentation. And if there's more questions, feel free, everyone, to put them in the chat and we'll return to them at the end. So we are going to move on to our next presenter, who will be Aktria Prasojo, a PhD student from the University of Glasgow, who will be discussing delta hydraulic geometry. So Aktria, whenever you're ready, go ahead and share.
Thank you, sir. I will full screen this screen. Okay.
Looks perfect.
Yeah. Hi, everyone. My name is Aktria Prasojo. I'm from University of Glasgow, as mentioned earlier, and I'm a third-year PhD student. I've worked with Trevor Hoy, Amanda Owen, and Richard Williams. So I will try to briefly explain what I've been doing in this past few months. It's about the down-delta hydraulic geometry and its application to the rock record. I know the hydraulic geometry, it's a pretty strange terms in our world as a sedimentologist, so I will try to explain it as briefly but as simple as possible to you. Okay, so we will start with a very simple concept. So if you have the source to scheme like this one, we have the hinterland as the catchment, and it will then transport all the waters through the conduit or through the river, and then sometimes it can be deposited here in the river system or more downstream part in the distal part here as a delta or estuary or anything you have there. So if we have a cross section around here, and we will have the water discharge at the low flow stage, we will have this channel width and this channel depth here, because the water is quite low at the time. So if you have quite higher flow or normal flow, the channel width will of course increase and the channel depth will also increase. When we have the maximum discharge or we have the bankfull discharge, the channel width will keep increasing and the channel depth will keep increasing as well. So that's basically hydraulic geometry. So the relationship between the hydraulic properties to the geometrical properties of the river system. So this kind of interrelationship will then create this equation. It's not really equation, it's just to explain that basically the water discharge is a function of the channel width, the channel depth, the velocity, and also the catchment area, because the bigger the catchment area in the hinterland, the bigger the discharge. So we can deduce to two simple equations as I mentioned here, where the channel width can be a function of the discharge and the catchment area can be a function of the discharge as well. This can be very interesting for sedimentologists because we have a very straightforward relationship between the discharge or paleo discharge that we are interested in from the rock record to the channel width or to the catchment area. So if we flip these equations around, we can then extract the channel width or the catchment area from the rock record, and then we can get the paleo discharge directly. So to image what I meant by that, so this is one of the example from the Ferron sandstone in the US. You will have several distributary channels of delta deposit here. As you may see here, I colored as blue here. We have 3 different distributary channels, so we can directly measure the channel with 3 different channel widths of distributed channel, and then get directly the paleo discharge from the rock record. This will be very interesting because if we reflect back to the literature, we already have from the fluvial systems, and I can show you here, but the main point that I want to deliver here, we don't have the one yet for the deltaic system. And when we try to apply from the fluvial to the deltaic, it will create a lot of problem because it can be in the delta system, we have different processes involved. We have the sea level, we have the wave, we have the tide, and we have all other marine influences that make the river channel can no longer have unidirectional flow of the water. So if you want to apply the fluvial system, that's one of the problem. And second problem, as well, as you may see on the equation on the right here, and as also just explained by Nikhil, you can say that all the equations here are quite complicated, and all the parameters that can be extracted from the rock record will not be straightforward, like the paleo slope, like the relief, and also the paleo temperature that you need to interpret the paleo discharge from the rock record. So the research question that I propose here, is it possible to predict the paleo discharge just from the channel width or the catchment area if we have that from the rock record, and it's specific for the deltaic deposit, and what are the limitations? So that's what we did basically from the modern system. So we try to compile 65 river-dominated deltas spread across the globe. So we have 5 different climate regions, and we get some data from the hydro basins as well to get the catchment areas and the global discharge datasets from the GRDC. Then we measure the channel width of the distributed channels of all those deltas, and we got around 2,300 channel width measurement from the Landsat. And then we run the OLS regressions to understand if there's a scaling relationship between the channel width and discharge, and also the catchment area and discharge. And then we will test that. We will try to apply that to the rock record and see how it goes. So our data look like these more or less. So in the left column, you can see the catchment area distribution. And on the right-hand side, you will see the channel width distribution. As you may see on the left column, the catchment area, it's quite a bimodal distribution and not so different. My data is in the color of pink here, and the other colors are from the literature, either from the delta system, which is the blue here, or from the river system, which is the red, dark red here, or the black here. So as you may see here, the catchment area has a bimodal distribution, and in terms of the channel width, it has positively skewed or right skewed channel width distribution. So using the median value will be more appropriate rather than using the mean value of the channel width, because it will be more statistically representative. And when I try to run the t-test, the delta catchment areas are not significantly different from the river system. But when we try to do the t-test on the channel width on the delta system are totally different from the channel width from the fluvial system. So that's why I say that we cannot really adopt from the fluvial system, the scaling relationships from the fluvial system to the deltaic systems. So from here, these are the relationships that I found in terms of the water discharge and catchment area. As you see on the top left here, this is the global discharge and catchment area relationship for river deltas. And here I then classified based on the climate. We have the arid, cold, tropical, and so on. So as you may see here, the global and the climate classified QA relationships are statistically significant, except in the arid and cold settings, because it's quite tricky there because we don't have quite continuous water discharge there. So it's a bit tricky to define the bankful discharge in those specific two climates. And when we try to compare that with the river system, I have the equations here for the global river as the red dashed line here. The global deltas Ka is not significantly different from the global river. So basically they work in the same way of in the river system. When we try to work on the water discharge and channel width scaling relationship, you may see more robust scaling relationship here, where you have the R square equals to 0.77. So statistically, it's quite high. And when we try to classify them based on the climate, they produce a better fit of its climate. But again, the weakest relationship comes from the arid setting. And when we try to compare that with the global river KW relationship, the global deltas is significantly different from the river system. So the most interesting part is when we try to test that, when we try to apply that to the rock record. So we compile three formations come from the Dunvegan, Ferron, and McMurray. The images here are from the Ferron sandstone. It's from the Cretaceous, and it was deposited in the subtropical and also tropical region. So as you may see here on the right-hand side, the blue bits are from the KW relationships, and the brown bits are from the Ka relationship. So when we try to plot that and compare that with the previously estimated bankful discharge from the literature, you can see that they're all in the same order of magnitude. But in this case, we use less parameters than other methods. So the other methods basically use the fulcrum trunk-based method to estimate the paleo discharge value of the deltaic deposit. So the process of using these equations it's already climate classified, and there are less assumptions and parameters needed when being applied to the rock records. You can try to measure the channel width from the rock record and get the paleo discharge almost directly. And the cons of this one, we don't take into account other variables that affect the discharge. So that's why we have quite variation or quite high standard deviation in terms of the scaling relationships that I showed earlier. And also to apply this, you need other contextual information gathered from the rock record. Either it's the grain size or the sedimentary structure to support your finding in terms of the paleo discharge. So what's next after this one? So basically it's just recently published on the right hand side here, but we already have the global river width from the Landsat, and now we have the global river discharge from the Landsat. So if we compile that, we probably can extend to other system, and then we can test that to other climates or to other age or geological age systems. So from here, as a take-home notes, basically we can use the hydraulic geometry theory to calculate the discharge or paleo discharge of the river deltas, and the relationship for specific climate zones may improve predictions, although larger data sets are required. And the rock record focused scaling relationship we propose here use much fewer parameters and assumptions than the existing scaling relationships such as the BCAR or the fulcrum. And the growth in global datasets enable this study. So we can then extend this study, or we can then test this study to other age system or to other river system that has the conduit or water flowing there. And I guess that's all from me. Thank you very much for listening.
Thank you so much, Aktria. That was fantastic. So my question for you while we wait for others to post in the chat is kind of a suggestion, but also what do you think of, it's really interesting, those relationships you see with the different climate zones, different discharge amounts. And I'm wondering for channel width, for changes in the distributary channel widths and things like that in different climate zones, what do you think might affect them the most? Is it the seasonality, or is it things like permafrost in the Arctic that might actually control what the style of your river system looks like and then your delta?
So in terms of channel widths, there's a study quite old in the 80s, I guess. So basically the bankful discharge in the river system, 90% is a function of the channel width, the channel depth, and also a bit of bank material and other parameters like sinuosity, braided index, will not affect that much in terms of the bankful discharge. That's why we try to simplify the parameters as simple as possible, because we want to make the rock record focus scaling relationships. So yeah, that's it. Thank you, Sarah, for your question.
And then my next one that I'm wondering is if you could have any field measurements in addition to, your wonderful global study, what would be the first one that you'd want to bring in to advance on what you're looking at?
So the one that we already tested here, as I show you, it's from the Ferron sandstone, the Dunvegan, and also McMurray. They're all deltaic deposit that really well outcrop there in the US and in Canada. That's why we tested from there. But it will be very interesting if you have the data from the subsurface delta, so we can also work to see in the other geological age system as well, if it fits quite perfectly like what we found in these 3 formations. So yeah.
No, that would be incredibly interesting. I like looking at that kind of upstream to downstream transition, and you can see what's going on there. Well, we'll keep the chat open. So everyone, please, if you can, in the chat box, please put a question for Octria. We can also return at the end if you have something inspired and you want to make sure you come to it. We will have a panel right there. I will ask one more question, Octria, if you will humor me and let me think a little bit more about this. We're working with some undergrads who are looking at grain size and trying to see how those change from upstream to downstream. Do you think looking at those changes, Nick Hill talked about having larger grain sizes in his amalgamated channels versus his singular. Do you think looking at anything like that might also advance your study?
It may be, but theoretically it won't be. So it depends on the scale that you're observing, because it was during the lockdown. What I can see is the satellite images. So the global data set we have is from the satellite images. So I guess that's why we focus on the satellite images, and what we can see from there. We can see the sinuosity, we can see the gradient in that, we can see the channel width and so on. So that's why we focus there. But theoretically, I'm not so confident with the change of the grain size, even though it's very important for sedimentologists. But yeah, I don't know.
Sorry, we like that. Well, thank you, Octria, so much. We will have time at the end. So anybody who's inspired by any questions and they want to put them in there, please, we will get to them. But we will move on to our next presenter, who will be Jing Liu, a PhD student from the University of Bremen, and she will be discussing Tasman leakage. So whenever you are ready, Jing, go ahead and share for us.
Okay. There you go. Thank you very much, Sarah, and hello, everyone. My name is Jing Liu. I'm a first-year PhD student at my home University of Bremen, and today I'm going to talk about my PhD project tracing Tasman leakage. So first of all, what is Tasman leakage? Tasman leakage is a water connections link Pacific and Indian Ocean at an intermediate water depth south of Australia. You can see here the East Australian current transport warm waters from Pacific Whirlpool southward into Tasman Sea, and parts of the EAC waters succeed around Tasmania, forming the Tasman leakage. The Tasman leakage flow in a narrow band into the Indian Ocean and pass the Broken Ridge. Here in this cross section, you can see the Tasman leakage has a core in between 300 and 1100 meters. And meanwhile, the Broken Ridge sits around 1070 meters below the sea surface. So the two study sites, namely OTP site 752 and 754, just bathed in the Tasman leakage waters. And half of the Tasman leakage waters join the Agulhas currents, and half of them just retroflect back into the Indian Ocean. So besides Indonesian through flow, Tasman leakage provides heats and return waters to the global thermohaline circulation via this Agulhas system. When Tasman leakage flowing from east to west, it maintains its temperature, salinity, density, and only has a little bit change on their water depth. So that is because Tasman leakage undergoes no to little mixing with other waters. For instance, Antarctica intermediate waters at south and Banda intermediate waters from the north. Here in this figure, a first order comparison of previously published benthic foraminifera data C13 datasets show around 7 million year. The data C13 signal from the Broken Ridge here converges with the data C13 signal from Tasman Sea. And it diverges with the data C13 signal from Antarctica intermediate waters. Well, this observations indicates around 7 million year onset of waters transported from Tasman Sea into the Indian Ocean and replaced the AIW itself. So let's move to sedimentologic evidence. You can see here in this complicated figures, although there are some sediment hiatus exist at the Great Australian Bed, the frequency and period of which increased largely since the late Miocene, which caused by more sediment removal that due to higher energy of currents. At the same time, a similar story happens in the Indian Ocean. House et al. Find the renoving signal at site 752 on the Broken Ridge, which also indicates an increasing currents energy. And here you can see the current winnowing signal shown in a black record has a good agreement with the potassium record shown in a blue curve by Hundfeld et al. And they use the potassium values as an precipitation proxy. So this figure indicates coupling between the currents energy and the paleoclimatic variabilities. As both geochemical and sedimentological proxies agreed in a late Miocene onset of Tasman leakage, my project aims to pinpoint onset of Tasman leakage precisely, say on an orbital resolution level, and also to test what is driving factor of Tasman leakage, whether it's because the southward migration of subtropical front or the northward motion of Australia that create a bottleneck effect of the Tasman leakage. So the main objective is to differentiate between Tasman leakage and the Antarctica intermediate water, which is relatively easy because A, Tasman leakage maintains its water properties, as I've mentioned a few slides before, and B, Tasman leakage is different from the AIW. Here we can see in this table, Tasman leakage is warmer and saltier, and delta C13 heavier than AIW. So now I'm building another benthic carbon stable isotope series, but in an orbital resolution. So here is the comparison between my work and the original work by Ria et al. In early 90s. The main difference between my works and her works is the original 5 data points you can here showing the original curve now covered by 200 data points. And the left 900 data points that will cover the whole record are just on their way. And I also would like to say something about the neodymium isotope. Although this proxy wasn't included in the original project proposal, I will have it as a set project, excuse me. So I encountered this beautiful, nice, well-preserved fish teeth when I'm picking benthic foraminifera, and those can be used to measure the neodymium isotope, which also serves as a water mass tracer that can help me to differentiate between the Tasman leakage and AIW. And also thanks to eCord, I got funding to test them next summer in Barcelona University. And hopefully I will got a record that follows the AIW and members, which shows in this right curve prior to 7 million years and looks similar as Tasman signal, this blue curve after 7 million years. The take-home message is Tasman leakage does exist. It's not just a conceptual model, and it is a really important component of oceanography because it distributes heights and water masses in a global level. However, it hasn't been well studied. So now I would like to further study it and pinpoint Tasman leakage on an orbital resolution level and to learn its dynamics. And I wish you like my talks and find it interesting. Thank you very much for your attention. And also I will have many thanks to my colleagues coming here to support me. Thank you.
Thank you so much, Jing. That was absolutely fascinating. So while we wait for some questions to come in the chat, I wanted to ask you mine first. I'm sorry if you covered this, but you were talking about the climatic influences, especially rain contributing to the potassium isotopes or elements that you were looking at. And what I'm wondering is, what about temperature? Did you say anything about how temperature at that time might have influenced? And just thinking about, you know, we had a lot of those hotter events occurring near that time. Would that influence any of the Tasman leakage at all, or do you not think so?
You mean the temperature itself that influenced Tasman leakage, or is the difference of temperature between Tasman leakage and other water masses?
Not so much between the other water masses. I know that's probably extremely important, but I just mean in general, globally, of that temperature at the time. Would that influencing, you know, anything at all, or no?
Well, I'm not really sure, but I think as is in the mid or let's say late Miocene, I don't think it has a big influence on Tasman leakage.
Perfect. So we're still waiting for some questions to come in the chat. I see one was put in for Octria, so we'll return to that at the end, Octria, if you'd like to respond to that one in person. Jing, while we wait, I guess my other question would be, you know, the same one I asked Octria. If you could get field measurements, you know, you have here your wonderful carbon isotope records. Is there anything else you would like to pull on top of the neodymium isotopes, the potassium, and the carbon isotopes to further explore some of these questions you have?
In fact, I also plan to measure the clumped isotope that will reveal the temperature change. And also I would like to use some basic assemblage to see the change of water itself.
That would be really, really fascinating. The clumped isotopes, I see them always being pulled into some really interesting studies. So that's a good one. You should try to pull that in.
Thank you.
Well, perfect. Well, Jing, we will also return at the end if anyone would like to put some last minute questions for Jing in there, and we will definitely have time at the end to answer them. We will now move on to our next presenter, who is Max Rollner, a PhD student from Curtin University, who will be discussing his new work with detrital zircons. Max, whenever you're ready, go ahead and share your.
Yes.
Perfect.
Can you see?
Oh, looks fantastic. Yeah.
Perfect. Excellent. All right. I will also talk about some of the work I did during my PhD, and the topic is source to sink. And the key process of source to sink systems is sedimentary recycling. And today I want to talk about how we can discriminate first the multi-cycle detrital zircon using Alphadose to essentially identify sedimentary recycling. So the reason why we should be interested in this because is the often quoted statement is zircons are forever. Essentially, this means they can survive several sedimentary recycling, which is generally good because they can inform us about a lot of things going on in the sedimentary system, but also it might be sometimes a bad thing because of sedimentary recycling. So they are subject to sedimentary recycling, essentially meaning the sediment gets deposited and gets re-exposed to erosion, and then enters the sedimentary system again. And this can potentially influence our source to sink interpretation, thinking of somebody interested in primary signals coming from source to sink. Processes along the way, such as sedimentary recycling, can influence this signal significantly. And this is relevant on the geological timescale, but also for processes occurring more on a more recent scale. So key challenge for people working with detrital zircon is to distinguish first cycle zircons, essentially coming from primary crystalline basement rocks, and multi-cycle zircons, which are sourced from sedimentary rocks. And today we want to have a look at the alphadose as a measure for sedimentary recycling. Alphadose is essentially just the number of alpha decays within a mineral. So it is a proxy for radiation damage, or people call it metamictization for zircons, for instance. And we can calculate this using the uranium and thorium concentration and also the age. Generally, the higher the uranium and thorium concentration and the older the age, or the older the crystal, the higher the alphadose. And with higher alphadose, we lose crystallinity. That essentially only means that high alphadose grains are less labile than low alphadose grains. So they, when they are subject to sedimentary processes such as chemical or physical weathering or transportation or storage, they are more likely to break down. So we want to use alphadose as an internal measure to detrital of detrital zircon to address recycling. And what we come up with is this metric called source-normalized alphadose. Essentially, all it does is compares the alphadose of individual detrital zircon grains to the alphadose, or to the average alphadose of source rock zircons. So we're comparing source and sink alphadoses. And the idea is that by this, we can track the selective removal of high alphadose grains during transport, because this is what we expect based on what I said before. And ideally, we get results close to this pointer, to this interpretation, where a value of 1 of this ratio would indicate first cycle, and a value below 1 would indicate multi-cycle and or transport processes affecting the detrital zircon populations. So we went to Southwest Australia, the Scott Coastal Plain. We've chosen this site because it has a well-established geology. We have in dark green the Pinjarra orogen, in red the Yilgarn Craton, and in blue the Albany-Fraser orogen. We took several samples of modern sediments, so we can actually observe the relationships of these sediments. We took samples from rivers. You can see up right here the catchments. The Blackwood and Scott are the largest, whereas the Nelly and Rollner are smaller rivers of that area. And also we take a transect along the coast to see variations along the coast. Then we separated zircons and dated them. I don't want to go in detail, but we used the most conventional approach, which is probably laser ablation. Here are the results of the geochronology. We obtained roughly 1,000 concordant detrital zircon ages, seen on the right-hand side. The x-axis essentially shows the age, and these kernel density plots, just the frequency distribution, and essentially the higher the curve, the more grains of a given age are present. And we see these 3 prevalent source rocks I've talked about before. In green, Pinjarra orogen, in blue, the Albany-Fraser orogen, and in red, the Yilgarn Craton. And straight away, we see that overall sediments are dominated by Pinjarra orogen derived zircon grains. Now the question comes up, what is first cycle or what is multi-cycle? But before we come to this, we want to have a look at the sediment dispersal system. So what are we actually looking at? And one thing that pops up quite quickly is when we compare the catchment geology, so essentially the areal extent of different source rocks. For instance, the Yilgarn Craton of the Blackwood River makes up to 90% here in red, whereas the age spectra only contains 10% of zircon grains derived from the Yilgarn Craton. The opposite can be observed for the Pinjarra orogen, which makes up like 80% of the age spectra, but only makes or accounts for 1% of the catchment area. So only this corner over here. And this might be a first indication of recycling processes going on in this river system. It might pick up all the sediments along the way through the coastal plain or through the Perth Basin. Also, the opposite can be observed for the smaller rivers, which reflect their catchment geology quite nice. And then a quick look at the coast, where we essentially have a longshore drift system active. We see a decrease of Pinjarra orogen derived zircons and an increase of Albany-Fraser orogen derived zircons in blue here. And the key thing to keep in mind for the next slide is that the sample in Augusta has been taken directly in front of the outcrop, so more or less as a proxy for sediments derived from active erosion, or something we would call then first cycle zircons, or would expect this to be, and then we can compare this to what happens along the coast. And now we come to the main results of this study. the source-normalized Alphadose values. So on the x-axis, we can see the different samples. And then we see in the 3 different colors, 3 different sources. This is just, again, the formula. So we normalized by the median of the source. And then we can look at the Blackwood River, where I said before, it has indications for active recycling processes, and we see values significantly below 1, consistent with what we would expect. On the other side, for the rivers, which reflect the catchment better, we see values close to 1. And for the sample in Augusta, which is set, which we would hope to expect something like first cycle signature, we also see a value close to 1. So maybe I should have said this is our box plot. So there are no uncertainties, individual populations with different percentiles. But what we then see is that we have this steady decrease from west to east, which we interpret as either the removal of labile grains or the incorporation of multi-cycle sediments along the way, which have spent more time in the sedimentary system. And now we could obviously look into comparing different age population, discussing things like preferential information loss to improve our interpretation. But we want to have a quick look at other systems. So these are all published literature data, and one example is from Japan, also modern sediment. There is the Takadani granite and the Azusa River, which essentially runs on top of it, and people have dated the zircons in the river and the granite. And when we compare these, make the source-normalized Alphadose metric, we get a value of 1. So more or less job done. This is what we would expect. Then we look at an ancient sample or an ancient sedimentary system. We look at Grenville-derived detrital zircons in the US. So this is one of the prime examples for sedimentary recycling, and people have used diogenic monazite to prove essentially these recycling relationships before. And we find a similar trend. We see this stepwise decrease of the 90th percentile, which we interpret as showing the removal of labile grains. Similar for the Perth Basin, comparing to the Blackwood River, where we also see a decrease, probably a bit less prominent, but also lower numbers here. So essentially, we can see this works on a different time scale, and also for published data, because these are the uranium thorium concentration are things we measure anyway with the Geochronology. And I just want to conclude what I said before. Right hand side is just the concept again. So we believe that source-normalized Alphadose can reveal selective removal of metamixed detrital zircon grains. Thus, we can document progressive sedimentary recycling and/or transport. We can apply this concept on different timescales, and we can apply this method also to already published uranium-lead detrital zircon data. Thank you.
Thank you so much. That was really, really interesting. And so while we wait for some questions to come into the chat, Max, I wanted to ask you, you mentioned a bit that you had accounted and thought about the longshore drift that was happening along this. I think this is a really clever way to take a look at some of these behaviors. And for, something ancient, looking back, 100 million years ago, would there be a way to maybe make hypotheses if longshore drift was influencing it all there? Or do you think, this couldn't give that resolution?
Well, if the field work doesn't help me, I think one way you could look at would be grain size or roundness, which essentially we also did or was requested by the reviewer. And essentially it proves our point. So we also see an increase of roundness from west to east with the longshore drift. So that would be a thing I would probably look at.
Okay, fantastic. So like in ancient samples, you would look to see, look at their grain size and roundness distributions and actually use that as kind of a investigation proxy.
Yes.
Very cool. Very nice. So while we still wait, I do want to make sure we actually have some time to return to a question that Aktria received, which I see you already answered in the chat, Aktria, but I'm going to make you, if you can come on and maybe answer for us. This was a question from Gary Hansen, who's from London, who is asking Aktria, how might scaling relationships be tightened up for delta systems developed under arid climates? And Aktria, if you're here for us, if you could maybe give the reply you gave in the chat.
Yeah, well, I'm really sorry because I saw the message after I pressed the send button. So I'm really sorry. So yeah, thank you, Gary, for your question. It's a very interesting question. In the arid setting, I know it's very tricky because in that setting, normally we have a very high flow, but only lasts for several hours. And then the river will completely dry. So it's very, very difficult to define which one is the baneful discharge. In our studies, we use the 2 years recurrence flood interval as the baneful discharge as used by many others. But if we play around, quote unquote, play around with this, what we define baneful discharge as a baneful discharge, we may be able to make a better fit for the arid setting. And of course, by increasing the data frequency as well, I already showed the global data set of the channel width and also the global data set of the discharge. If we compile that, we of course will then make a better fit of the arid setting. But I know it's quite tricky, especially if we want to translate it to the rock record. It's not that straightforward, but yeah, thank you, Gary, once again.
Thanks, Satya, for letting me put you on the spot. So Max, we have a question for you here, which is from Guido Pastore, who's from Milano. And he says, at which scale do you think you can apply the alpha normalization? How can you decide the right source, median, alpha dose in big catchments?
Yeah, thanks for the question. With the scale, I would say this tool, or at least how we perceive it, it would be like first order idea to generally look at. I mean, if I compare different sedimentary packages, I mean, I can obtain first order relationships. So that would, if that answers the scale, and deciding the right source, I mean, essentially you need to be quite sure. And ideally, what we also have for this study, having other information telling us essentially this is the right source. So we collected hafnium isotope data, and we were anyway in a spot where we know the geology quite well. So you should be sure about the source, and it's obviously a key assumption. And I guess generally the better the source is constrained and the smaller the variation within the source, the better it is. I hope this answers the question.
Thanks so much, Max. And thank you to all our presenters who gave absolutely wonderful presentations, really, really exciting, so many different tools going into those. So these are all presentations that focused on the theme of sediment transport from source to sink and kind of our new investigations. And so, certainly thank you all for listening. If you have questions, feel free to send them to the SEDS Online team and we can send them to the students. Please, we do have a few more minutes if you want to put it in the chat. And if not, thank you so much to everyone for listening. A huge thank you again to our wonderful presenters. You guys were all absolutely wonderful. And thank you so much for your time and your beautiful presentations, beautiful figures as well.